Hello, everyone. My name is Craig, and I'm again going to be your host for our final Apollo Recreated virtual training. I'm located at our Exton, PA headquarters with Shannon and Patrick. They're going to be our engineers answering those questions for you today. And then Austin is going to be, he's on my left. You'll see it on the video. Again, he's on my left. And he's going to be the one taking you through the training. This training does require 11.6, and if you do not have 11.6 installed, we do have an STK web feature. It is browser-based, and it is the details for getting the STK web up and running are in the chat panel. So please take a note, and if you need 11.6 and you don't have it installed, you can use that. We do encourage questions, so if you're falling behind on something that Austin taught, please ask using that questions panel. Somewhere on your screen, you should see the GoToWebinar window. And in that window, there's a questions panel. When you ask that question in that panel, we will try to get to it as quick as we can. All right, Austin. It is all you.
All right, thank you, Craig. And thank you, everyone in attendance today. Thanks for coming to our part 3, our final part of recreating the Apollo 11 mission. If you haven't already, please go ahead and download the recreating Apollo.pdf. That's been updated and added the third part of the training, which we'll go through today. And make sure you have STK up and running, or if you're going to be using STK as a surface, go to licensing.agi.com/training, and then click STK as a surface. Pick which East Coast or West Coast, whichever is applicable for you, and go ahead and start STK now. All right, so once you get that up and running, I'm going to go ahead and bring up my PDF. The first thing we're going to do is download the scenario, and that's been uploaded to the SDF. We have 2 versions. We have one with imagery, and it's called Recreating Apollo 11 Part 3.vdf, and then we have Recreating Apollo 11 Part 3 with imagery. What we did since last time is we made the file size just a little bit smaller. It was about 1 gig last time. This time it's about 250. And now it only has local terrain, a little bit higher resolution around the Apollo landing site. We didn't give you the whole global moon, so it'll be a little bit faster download and it'll look a little better. So go ahead and download the Apollo 11 Part 3, or go ahead and try the one with imagery, which is Apollo 11 Part 3 with imagery. The way to launch that from STK is go up to here to the top where it says File, then Open. Click on SDF, and then after that we're going to click on the tab Browse once it appears, and then we'll navigate to the link in the training manual, which is Sites, AGI Support, Apollo 11, and now there are a couple in here. Again, we're looking for Apollo 11 Part 3 VDF or Apollo 11 3 with imagery VDF. There's also the completed version, so if you do miss a step today or something's not working for you, the completed versions have been uploaded there. And one last thing I wanted to point out, under this page there is a user homes, and then there'll be your associated email for your AGI login. If you want to access this scenario in the future and you don't want to save it locally, you can save it to your email link, so you can come back and view this later, and that'll be linked with your AGI email. All right, perfect. I'm going to go ahead and save this locally. So open up the Apollo 11 Part 3 with or without imagery. I already have it open on mine, and this is what it should look like. So last time we left off with the moon landing. We landed, and then after we landed on the moon, the astronauts spent a couple hours and they performed one EVA, or extravehicular activity. And as we all know, Neil Armstrong stepped out first with his one small step for man and one giant leap for mankind. You can actually jump to the scenario when that time took place in the stored views dropdown. And then if you click on Armstrong's first step, you can see we landed at 4 days, 6 hours, 45 minutes. And then about a little less than 7 hours later is when Neil took his first step. And while they're on the surface, of course, they planted the flag. They had a call with Richard Nixon. They set up a few science experiments. The whole experience only lasted about 2.5 hours. Buzz Aldrin joined him, and then they got back in the lunar module. So today we're picking up when they are about to take off. So if you want to go ahead and jump to the lunar ascent, actually go back and jump to the Armstrong's first step. The lunar ascent stored view will pop up once we go ahead and build it. So all in all, the crew only spent actually about 22 hours on the surface. 2.5 hours was for the extravehicular activity, and now they are about to take off. So go over to the left-hand side of your screen, the object browser. I have mine auto hidden, so it actually hides when I'm not using it. But go ahead and click on the object browser. Right-click on the Lunar Ascent module, then open up its properties. So what we're going to do first is edit the follow descent segment, and that is following the currently set to follow the service module. What we're going to do is update that, and we're going to change that to the lunar descent module. So the ascent stage is just going to follow the descent stage down, and now what we're going to do is update its joining and separation conditions. Those times of 5 days, 4 hours, and 22 minutes are located inside the PDF on page 37. That's the beginning of this training. So go to the Recreating Apollo 11 PDF, copy that first value, 5 days, 4 hours, 22 minutes, copy and paste it for the joining, and then do the same thing for the separation. And just like last time, we could have joined the Ascent module at the beginning of the mission, but in order to cut down on extra ephemeris, we went and just joined them at the instant that it left the lunar surface. Okay, so the next thing we're going to do is go ahead and configure the mass of the lunar ascent stage, and the dry mass is a little bit beneath it in the PDF, and that's 2,445 kilograms. So click the spacecraft parameters, update the dry mass section. And then we're going to scroll down just a little bit, and we're going to update the maximum fuel mass and the fuel mass on the next tab over on the fuel tank. And then that was 2,376 kilograms. So update both the maximum and the fuel mass there. And then we're going to go move on. So now we've configured when it's leaving as well as its mass. We've all set up this configuration. It follows the lunar descent module. The next thing we're going to do is go down to this first target sequence and then click on lunar liftoff. Now we need to have the liftoff phase start in the right location. So what we're going to do is, by default, the central body is Earth. We're going to adjust that, make that the moon. So double click those ellipses next to Earth. Then we're going to click moon. And so we're actually lifting off from the moon and not the Earth. So all these latitude values are with respect to the moon. And then instead of updating all the latitude, longitude, altitude like we did in a previous section, we're just going to click this button right here that says use state from previous segment. So it's just going to start where the previous segment ended, which would put it in the same place as the lunar descent module. So you're just going to update this use state from previous segment and make this central body the moon. Okay. Next, we're going to move on. Right beneath the lunar liftoff, there is a remove fuel mass. So that's an update segment inside STK. It's going to, in this case, update our fuel mass that is representative of all the fuel being burned after the lunar liftoff. So what we're going to do in this case, instead of actually subtracting all the values off the fuel mass, one trick you can do is actually take a little bit off the dry mass. Still represents the fuel mass, but you can take it off the dry mass. And the reason for that is because sometimes in the later target sequences, when you're running low on fuel, as it's iterating around, sometimes it'll find solutions that use a little bit too much fuel. And instead of saying, no, those are no good solutions, you can allow the targeters to use that information. So again, instead of avoiding that targeting difficulty problem, we can just take a little bit of the mass off the dry mass instead of just the full 2,200 kilograms off the fuel. Okay, so click on dry mass, change the action to subtract value, and then put 1,000 kilograms for the value. And then you go right beneath it, click on fuel mass, click subtract value, and put another 1,192 kilograms. So the mass loss from the fuel was about 2,192 kilograms in that ballpark. And then, as I just explained, we're going to take a little bit off the dry mass instead of it taking off the fuel mass. Perfect. All right, so let's see what that looks like. Go ahead and grab this stop segment, the move as needed, and we're going to drag and drop it beneath this first target sequence, but right above the target co-elliptic sequence initiation. Once we have that, go back and look in STK. I'm going to click the green run button. And it looks like we converged. You can see those red lines starting to pop up. I'm going to go ahead and close this target panel. Then click the clear graphics. And then click apply. So if I'm coming back to my 3D window, I'm going to jump to the stored view called Lunar Ascent. Here we go. And if you downloaded the PDF with imagery, you'll see this surrounding terrain. If you didn't, it'll be a little bit, it won't be nearly as detailed. Okay, so here we go. So we have the Lunar Ascent. I'm going to also, before I go ahead and animate, I'm going to click on the object browser and then go find the Lunar Descent module and then uncheck the Lunar Descent module. The reason for that is there's this data display over up in the left-hand corner, and we just want to get it out of our way. We could go and uncheck the data display, but it's just a little easier to uncheck the Lunar Descent module entirely. Okay, at this point, we're going to go ahead and hit play, and you'll see the Lunar Ascent module take off. There we go. So the crew are on their way up, and this is going to put them in a lunar orbit. It is about 9.4 by 48 nautical miles. It's an elliptical orbit. So what they're going to do after this is a series of burns where they will increase their paraloon, and then they will do a series of burns to slowly raise their orbital altitude in rendezvous with the command module, which is in orbit around the moon with Mike Collins. One other thing I wanted to point out real quick is if I go back to that Lunar Ascent stored view, is right around here. Actually, in the when I was recreating this for the entire mission with the one with terrain, there's actually a little mound right here, and what that little mound was the actual Lunar Descent module. So there's an orbiter called the Lunar Reconstruct orbiter, which is orbiting the moon today, and you can actually see an image of the bottom of Eagle, as well as a little mound that's actually captured in the topography that actually got lumped in with the terrain. So that was pretty cool when I was recreating this with the version with terrain. Okay, continuing on, let's go ahead and save our scenario. So if I go to File, Save As, you can either save your VDF to your local your email, which is registered with your AGI.com, or you can save it locally. I'm going to save mine locally under my STK, my documents. This is my STK user area, STK 1164, and then recreating Apollo 11 Part 3. And then I'm going to change the save as type to be scenario. And I'm just going to click save. And if it says replace, yes, I'm just going to go ahead and replace it. Perfect. All right, so moving on. So now we've lifted off the lunar surface. The crew, Neil and Aldrin, are in about a 10 by 48 nautical mile elliptical orbit around the moon. The next thing they're going to do is something called the co-elliptic sequence initiation. This is going to raise the periapsis. And before we jump into that, I'm just going to go ahead and give you a summary of what they're about to do in the next couple burns. This is from the Apollo 11 mission report. It's linked in the PDF. So we have just lifted off the moon. They're going to go to this point 3 right here, perform something called the co-elliptic sequence initiation. And basically that sort of circularizes the orbit and brings the periapsis point up. They'll then do a smaller burn called the constant differential height to kind of match the eccentricity and account for the command module's orbit, the fact that's not a perfect circle. And they're going to line up the orbits, do a small adjustment there. And then they'll start a series of maneuvers over here, this 5, 6, 7, 8. The 5 is going to be the terminal phase initiation. That's just going to bring up the apoapsis just a little bit to match the command service modules. And then these next couple series are going to be the 6, 7, and 8, which are going to slowly slow the speed down relative to the command module so that it's going to approach just ahead of it in lunar orbit. And then once they get there, they'll spend another 16 minutes or so to actually go and dock with the command module. Perfect. All right, so we're on page 39 of the training manual, and we're going to go back into the properties of our Lunar Ascent module. So back in the properties of our Lunar Ascent module, we're going to click on the co-elliptic sequence initiation maneuver. And we're going to do a few things. The first thing we're going to do is go to the engine tab. We've already have all this pre-configured to be relative to the moon. We're going to click on the engine tab. And then for the engine model, instead of using the constant thrust and ISP, we're going to switch that with the ellipses button. And we're going to use the Lunar Ascent constant thrust. And then for the thrust efficiency, we're going to change that value to be about 5%, so 0.05. And then we're going to do one more thing, which is change the effects and acceleration, the thrust, to both the thrust affects the acceleration and the mass flow. So what that's doing is the Lunar Ascent stage actually didn't perform this maneuver. It was the RCS on the Lunar Ascent stage. There were 4 pairs of 4 thrusters moved around the Lunar Ascent stage, but it turns out that they have pretty similar ISPs to the Lunar Ascent and constant thrust. So instead of creating a new engine model, we can actually just lower the thrust efficiency, and by checking this mass flow rate option, it'll account for the mass change as well. So instead of building a new engine model, in this case, I'm just going to lower the thrust efficiency, and the mass will be proportional to this thrust efficiency change. If I didn't change this option down here, the mass used would still be the nominal 100% of the fuel, whatever it calculated. So in this case, I'm using less fuel by just changing to about 5% to represent the RCS or thrusting. And what I could do if I really wanted is I could create a thruster set and go and model each of those directions for all 16 of those RCS components. But it really wouldn't affect the mass too much. So we're just going to use the 5% here. All right. That's just a little bit of a trick you can do if you want to have to keep on creating new engine models. Okay, so go ahead and click on the target co-elliptic sequence initiation target sequence, the ones that's housing this maneuver segment. Open up the properties of the differential corrector, and let's quickly look at what's in there. Similar to the last couple times, we're going to be varying the direction of our burn as well as our thrust efficiency, and then we're going to end up targeting the altitude of apoapsis as well as the altitude of periapsis. And these values came from the Apollo 11 mission report. So if I open that up and jump to what I have from the Apollo 11 mission report. This is the co-elliptic sequence initiation. You can see the lat longitude values as well as the altitude and a couple of their values. If I scroll down just a little bit, there's another summary for the co-elliptic sequence initiation. This one's a little more detailed for the lunar rendezvous. And it said their end result was a 49.3 by a 45.7 nautical mile orbit. And that's the same thing we're targeting here. So that's where I got these values. We'll go and compare these a little more closely at the end. We're also targeting a longitude which kind of represents part of the end location of the orbit once it's done, as well as a direction. There's also this little hidden toggle inactive tab. If you click that, there's a few other values that are in here. They're not being actively targeted, but you could compare them to the actual results from these values. All right, now I'm just gonna toggle that back on, then click OK. So moving on, we've just went and looked at what's inside this targeter. If I scroll down to the next part, which is the constant differential height, it's going to be a similar setup. If I look at the constant differential height, it's using the VNC moon axes. These as an L are going to be targeted. If I look at the engine tab, it's already pre-configured. I have a smaller guess to account for the fact that it's RCS. That's all pre-configured. Same sort of setup with that guy. All right, so that brings us to the next part, the terminal phase, which is where they're actually going to be raising the altitude of their apoapsis to match up with the command and service module. And then they're going to be doing a series of braking burns to slow down the speed relative to the service module, as well as increase the periapsis. So that's what those braking burns are doing there. These values in this sequence, I got all that from the planned Apollo 11 mission report. So this is also linked in the PDF. This is right here, this Apollo 11 mission plan table 1-2. So that's what this looks like. I'm just going to zoom in just a little bit. So we have a time as well as how long the burn was supposed to happen and how big the delta V was. We had a first braking, a second braking, third braking, fourth braking. So I've added all those in here at the approximate time. And since these maneuvers were pretty small, and then this was the planned and not necessarily the actual delta V's that came out, they're going to be still pretty close. I just modeled those as small impulsive changes, but we could go through and model them as finite. It wouldn't have too much of an effect. But I have these small braking maneuvers here up until the last stage. So to show you once again where we're at, it is now this 5, 6, and 7 of this diagram right here. So raised up, and then these braking maneuvers are in this phase. And then the last bit, this target TPF in the command, in the mission control sequence, is this 8 and 9. That's when they're really going to stop right in front of the service module. Okay, so if we click on target TPF, that is something we're going to need to edit. So the end goal of this is to stop right in front of the service module. It's about 100 feet or so in front is in the lunar orbit is where they stopped, and then go up to terminal phase. So not target TPF, but terminal phase. So click on this terminal phase differential corrector, and here we're going to add the values 0, 100, 0. So the reasoning for this, the terminal phase is kind of this whole sequence of a bunch of braking maneuvers, and at the end of everything, we want to make sure we stop in front of the command and service module 100 feet. So at the end of this whole sequence of events, we want in 100 feet ahead. Go ahead and click OK. The target TPF, what that is that last little burn. That last little burn to actually bring them right when they're approaching to stop in front of the command and service module. What we're going to actually do with this one, we're not going to target the end location. We're going to target the rate. So if you go to terminal phase final, at this point we are page 41 of the PDF. We're defining the results for target TPF. Click on the maneuver and then click on results. So the radial cross-track and in-track are already set up in there, just to remind us that they're going to stop 100 feet ahead. But we're going to add different ones now. So if you scroll down to relative motion, we're going to add over 3. We're going to add over, and make sure you click the right ones here. So there's a couple in-tracks. Click in-track, rate, moon. So again, this is the in-track. Now it's a rate, so it's the velocity component, and then it's respect to the moon. So move over in-track rate moon. We're also going to move over cross-track rate moon. And then lastly, we're going to move over radial rate moon. All right, so you should see 6 in here. We're only going to end up using 3. But you should have in-track rate moon, cross-track rate moon, and then radial rate moon. Then we're going to click OK. All right, now we're going to configure target TPF. If you click on the differential corrector for the target terminal phase finalize, that's what TPF stands for. We're going to check cross-track rate moon, in-track rate moon, and then radial rate moon. The other ones are just there for reference to keep in mind that we're stopping 100 feet in front. But for this, we want all the rates to be pretty much 0. So if you click on cross-track rate moon, the default tolerance is like 0.1 meters per second. We're going to change this to be 0.001 feet per second. That's our cross-track rate moon. And do the same thing for the in-track rate moon, 0.001 feet per second. Same thing for the radial rate. It's going to be 0.001 feet per second. And the reason for that is when we say we're going to end our relative motion with respect to the command and service module, we really want it to end within tolerance. If you end and it still has a couple feet per second, over the next couple minutes or hours, it'll drift away. So when we ask this target sequence to target a stop, we want it to stop. Okay, I'm just going to click this hide inactive so you can see what we're targeting. In-track, cross-track, and radial all rates with respect to the moon. And then all the tolerances are 0.01 feet per second. All right, perfect. Then we're going to click OK. What we're going to do now is move this stopping condition to the end, and then we're going to configure one last sequence. So come up and grab the stop move as needed all the way to the bottom of your MCS. We're just going to drag this down all the way to the bottom underneath prop to end. And these last couple segments here are called target docking. That's once they actually stop in front of the command module. They perform a maneuver to a couple of small maneuvers to come and rendezvous with the command module itself. Then after that, the two will be docked. That will be this hold segment right here. And all we're going to do for that guy is we're going to change the hold frame. By default, I believe it's going to be the Earth Inertial or Earth ICRF. What we're going to do is click this ellipses button and change that to be the service module body frame. So what we're doing now is we're holding the Ascent stage constant with respect to the service module body frame. We're docked, so there's going to be held constant. Okay. And then they'll be held together for about 2.5 hours. Then it'll be let go and left in lunar orbit. All right. We are going to be done with the Ascent stage. So if you click Apply, let's come back over here and then run our MCS. So as a recap of what we just set up, we were in this elliptical orbit. They burned to raise their periapsis to this point number 4. They did a small adjustment. They then did a series of braking maneuvers to stop in front of the lunar module rendezvous, and they're going to end and kind of get rid of that the rate. So get rid of the in-track, cross-track, and radial rates, and then they'll perform very small maneuvers to actually come in and dock with the command service module that's in orbit. One thing you'll note is in the MCS, as this is running, there's actually 2 target sequences within each other. You can have that in the in Astrogator. There's no problem with that. It'll just say that this target TPF just keeps on getting run every time the bigger loop gets run. All right, it looks like mine converged, and then it's propagating to the end down here. and then I'm going to click OK. To close all these target sequences, I'm just going to left click on this target symbol and then click Close All. And then let's go ahead and zoom out a little bit and see what that looks like. You can see all these orbits. I'm actually going to go back to the Lunar Ascent module, open up the properties real quick to clear the graphics. Don't want to see all those. So I'm going to go back to the Lunar Ascent module and then click Clear Graphics, then click OK. And then let's go click on the stored view called Lunar Ascent Summary. So we can look at it from a slightly different perspective. Last time we just ended off with the launch. Go ahead and hit play. You'll see that the crew are then going to stay in this elliptical orbit, and they're going to go around the moon until they hit the other side right over here. This is going to be point 3 in this diagram. Then they're going to perform the co-elliptic sequence initiation. You'll see a little red segment. Yep, there's a little quick red burn that actually raises their periapsis up. And then from there, they will come over to the other, back to the sort of the original side, this point 4. They will perform a small maneuver. It'll turn red for a moment there, right there. And that's to sort of align the orbits. And then they're going to come around, start the terminal phase initiation, and then perform a series of small braking maneuvers so that these guys line up at the very end. Okay, then I'm going to hit pause. Let's see what other stored views we have. Click on Lunar Rendezvous. And you can watch the last couple moments of the Lunar Rendezvous, the sort of the TPF once they get close. And if you click play, you'll see the Lunar Ascent module come up and stop right in front of the service module, about 100 feet or so. All right. And then if we click pause, over the next few minutes, this Lunar Ascent module is going to come in slowly and rendezvous with the service module. So if I play that, it takes a couple of minutes, so I'm just going to speed up a little bit. But the Lunar Ascent module and service module will come in, and then they're going to dock. This actually happened when they docked. It was about 0.1 feet per second. Mike Collins actually said he didn't even feel them dock, and he thought they were going to actually have to separate and come back together. So these rates are really slow when they actually docked. So Mike Collins didn't even know they hit, and he thought they were going to have to separate and come back. But once they hit a couple seconds later, there was a little bit of vibration between the two spacecraft. And then a couple seconds after that, the latches actually locked, and then the two spacecraft successfully rendezvoused. All right, so we've got the Lunar Ascent stage back into orbit with the service module, command service module. At this point, the crew are going to transfer, so Aldrin and Armstrong are going to go into the command module. So let's go ahead and open up the command and service module. So let's go ahead and open up the properties of the service module. We are done with the properties of the Ascent stage. And we're going to carry on with the PDF. So we went through the summary. We can real quickly run a maneuver summary report, and then we're going to carry on with the mission. So I tricked you guys. We're actually going to open up the Lunar Ascent module real quick, the properties, and run something I want to highlight. And this is a maneuver summary, not a maneuver summary report, but a segment summary report. So if we click on, let's say, this co-elliptic sequence initiation, we're going to click on the summary report, which is this button right here. And this guy's going to pop up. If I scroll down just a little bit, I'm going to scroll down to about the fifth section or so, where I get something called integrated inertial delta V reference at the start thrust vector with respect to the VNC, or the velocity normal conormal of the moon axes. And then if we look at these values, we get an X of 52, a negative Y in the teens, and a very small Z component. If I go look at the Apollo 11 mission report, there's actually a table that has all the values that were actually used. So this is in a velocity normal conormal frame, pretty similar. It says the ones that they thought they fired were 51.6, a pretty small in the south and down. In our case, our velocity matches up pretty well. We might have had a little bit of a sideways movement there, but that's still pretty small. So I went through and checked all these values, and I got pretty similar results to all the values listed in the Apollo 11 mission report. So that just was a quick verification that, hey, we're on the right track, and these are being modeled pretty accurately. Okay. And so you can do that really for any segment. You can right-click on it and then click Summary, or you can just click this little Summary button up at the top once it's selected in the MCS. Okay. We're going to close the Lunar Ascent module properties. Then we're going to open up the service module properties. And then the service module is going to take us home. So carrying on with the training, we are on the journey back to Earth. So all the crew are now in the command service module. They're going to leave the lunar module in orbit, the upper stage, because there's no point in carrying that mass back. For museum purposes and historical reasons, they wanted to, but it didn't make any sense from a mass perspective. So we're just going to quickly look at the next couple phases. There's something called target trans-Earth injection. This is going to be very similar to the translunar injection and the lunar orbit insertion. It's a big burn that takes about 5 minutes. They're on the far side of the moon, so they don't have contact with ground control when they perform this burn. So ground control actually doesn't know, did this burn go properly? Only the astronauts know. So this is a pretty key critical moment. Sure, they landed on the moon, but it's still really important that this service module engine performed properly, or else they don't get home safely. As we know, luckily everything went fine, and ground control confirmed that they're on the right trajectory on the way back. So that was great. Okay, so that is what they perform next: a big burn to come home, trans-Earth injection. They propagate to about halfway to something called MCC2, or the second mid-course correction. This time they're also doing the barbecue roll on the way back home. And then the final bit down here is targeting the mid-course correction, targeting those values so that they come in and re-enter at the correct location. So we're going to change one thing in this service module, this thing called just for targeting. It's actually a return segment. So I'm just going to show you what this is. You don't have to do anything here, but if I were to go to insert before, this is a return segment. This just for targeting. I'm not going to actually insert anything, but we have the just for targeting here. And then I'm going to click close. And what this is used for, you'll see three options. This segment returns control to its parent sequence. By default, it's going to be enabled. And what that does, it says this return segment acts as a normal return segment would. But there's other options that said disable, so just kind of ignore this segment. And then there's one more that says enable except for profile bypass. And actually, that's the one we want to use here. And the reason for that is we are going to adjust this mid-course correction so that the command module, and not actually the service module, re-enter at the desired location. So what this allows this target sequence to do is propagate these two segments beneath it and adjust those, but not actually run it once we run the rest of the MCS. So it can target with these two segments down here, this command module only in the prop 2 CM reentry. But once it converges and finds a good value, it'll skip over these and then continue on. So that's what this enable except for profile bypass does. All right, from that, we're going to grab this stop, move it all the way down to the end of the mission control sequence. Then we're just going to go ahead and click run. And you'll see a couple target sequences pop up. These are all converge. You could have alternatively clicked the run only changed, and that would only rerun the new segments. But I went ahead and clicked run. So you see a bunch of the old target sequences that we already went through all the process of getting to the moon. And then you'll see one called trans-Earth injection, start targeting. And then the second mid-course correction will start targeting. And then once these converge, we'll end up just go ahead and closing all these target sequence windows, clearing the graphics, and then we'll just go ahead and save this scenario. All right, so click the target button and then click close all. Go ahead and click clear graphics in the service module. We're going to click OK. And then go ahead and save your scenario, file save. And then let's just hop through some of what we just went through. So that was a lot. That was about 3 days of the mission that we just jumped through real quick right there. Go to the moon view and click on trans-Earth injection. And if you animate, you can watch that guy. So they're on the far side of the moon. They can't actually see Earth. And then as they come around, mission control will see them, and the DSM will talk to them, and then let mission control know quickly whether they're on the right track or not. And again, luckily everything went not pretty close to nominally for this mission, and we all know they made it back home safely. So this is trans-Earth injection, and you can see that there. It'll take about 3 days before the crew get back. If we switch over to the Earth view, so not this moon, but the Earth 3D graphics window, click the drop down in the stored views. And so we have different stored views for the Earth. There is something called the command and service module separation. Go ahead and click that. That is where we are left off with from the most recent MCS run. It should look like the figure on page 45 of the PDF. The service module is about to re-enter. They're about right over Australia, and then they're going to end up coming and splashing down off the coast of Hawaii, just to the west, about 900 nautical miles or so. Before we do the splashdown and the re-entry, let's do a real quick maneuver summary report. So if I go back to my object browser and I right-click on my service module, there is a report and graph manager. Go ahead and open that up. I'm just going to go ahead and minimize my favorites and my styles and open up the Recreating Apollo 11 styles here. Actually, I'm going to just go with the installed styles. We'll use this Recreating Apollo 11 styles in a little bit. Expand the installed styles, and then if you scroll down to the maneuver summary report, and just go ahead and run that. This is a quick way to see the maneuvers of your mission, as well as the name, their start time, their stop time, their burn duration, their finite burn, their burn duration again. One's an estimated, one's an actual. The delta V that occurred, and as well as how much fuel they use. So this is the fuel budget for a mission. And if I very quickly open up the Apollo 11 mission report, I'm just going to hop to another page that has these burns listed. We have the values listed in this report. One of these other tables has a slightly better, more summarized version, but I'm just going to run off this one for now. You can see that these are all for the lunar module. I'm going to hop to a different section. And I just want to real quickly compare these values with what the values from the actual mission report. That's what I'm going for here. And then I believe these, okay, there we go. Table 5, 6, and 7 of the Apollo 11 mission report. and you can see this delta V. Here we go. This is for the trans-Earth injection. It was 3,279. So if I come to this report right over here, those are on feet per second. So what we're going to do is change this delta V value in the mission report. We're going to change the units from the default from meters per second. So I just right-click on this delta V, change it the units. We're going to change it to feet per second so we can make a more direct comparison. The values we found were 3,276, which is very close to 3,279. There was a small 5 feet per second, a mid-course correction. You'll see they found another 4.8, about 5 feet per second. Correction there. Their velocity changes if we come up and look a little bit earlier in the mission. There was this 2019, and that was for the lunar orbit insertion. And you can walk through this and kind of match up the values, and these all match pretty closely. So that knows that let me know when I was modeling this that we were all on the right track. Okay, so let's model the reentry. Now we are done with the service module. We're going to switch over to the command module, open up its properties. And we're only going to change one thing in here. So back to the PDF. This is on page 46, on the top of page 46 of the PDF. We're going to scroll down here to the first target sequence called Target Reentry Conditions. And then we're going to click on this maneuver called Lifting Force, and we're going to change a couple things. First thing we're going to do is change the propagator. So if you click the ellipses for lifting force, we're going to change it from the default, which is Earth HPOP default, to Earth reentry propagator with the double E's. And then we're going to go right beneath it to the velocity co-normal with respect to the Earth, this thrust axis, and we're going to change that to be the satellite RIC central body fixed thrust axis. And so what this is a lifting force. So as the Apollo crew are re-entering the atmosphere, the command module actually has a lifting force of about 0.3 with respect to the drag ratio during this re-entry process. They're coming in at a shallow angle of about negative 6.48 for the horizontal flight path angle. And during this entire experience, they experience a 6.56 G-force. In order to actually not land and dive too deep into the atmosphere, we have to model this lifting force in STK. In this case, we're sort of just doing an average lifting force. We're not going to the detail of making it proportional to lift and drag, but we can add in sort of the net effect of the lifting force to land in the right location. So that's all we're setting up here. And lift is going to be mostly radially away from the Earth. So that's why we chose these RIC central body fixed axes. All right. That is all we're going to end up doing for this mission control sequence. Then the drogue chutes are going to deploy once they get low. And then we're going to have a target sequence to vary the amount of drag they have from the parachutes for the final landing. So if you grab this target sequence, we're going to drag it down all the way down to underneath wait on recovery. Then we're going to click run. And so this is just playing with that lifting force value just a little bit, as well as modifying how much the coefficient of drag from the reentry. And then this last target sequence is playing with how much drag that the parachutes provided so that they splash down in the ocean at the right time. All right. Once your target sequences converge, you'll probably get this impact warning. That's exactly what we want. We want the crew to splash back down on the Earth. So click OK. That's great. Our crew are now safely back on the Earth. Go ahead and close the target sequence windows. Click the clear graphics. Click OK. Let's jump through what just happened. In this drop down, go ahead and click on reentry, and we can watch them come in. So the service module is behind and lower than the command module. And you can watch the command module fly in. the service module was actually supposed to skip out of the atmosphere. So the fact that it came in, it was actually caught on camera, was an anomaly that wasn't really expected to happen. But the service module did dive bomb back into the atmosphere. The command module did that as well. And they come in, and you can see them. It'll start to drop. This is right before dawn, right before the sun comes up. You'll see that they almost look like they're going to overshoot it, but actually the drag really starts to kick in, and they start dropping down to the splashdown location. So if I pause and then jump to the next stored view, the parachute deployment, this is how low they were when the parachutes actually came out. A little before this at 24,000 feet, so somewhere around here, the drogue chute came out. And then finally, splashdown. So now the crew have made it back home. One of the most historic events that's happened. They've landed down safely. So now what happens, they are greeted by the USS Hornet, which is an aircraft carrier, multiple aircraft, multiple helicopters. We've modeled 2 of them here. One is called the Swim 2, which is the helicopter that's going to rescue them. They're going to come in. They're going to drop off isolation, something called BIGs, the biological isolation garments. Back then, they're really worried about the lunar germs. So they came in, and we can go ahead and hit play here to see that. But you'll see Swim 2 come in. So this is a helicopter. Swim 2 is because they're going to have swimmers are going to jump out of the helicopter. The Navy frogmen are going to jump out of the helicopter. They're going to lower down right in front of the command module. They'll jump out, and then they will secure the command module. They will drop down life rafts for the crew to get into. But before that, one of the Navy frogmen is going to come up and put these isolation garments, open the hatch, and then give them the isolation garments, close it, let the Apollo crew don those isolation garments. Then they will crawl out where another one of the Navy frogmen is going to come down and wipe them down with decontamination materials. And at that point, they will be hoisted in kind of a seat up into the helicopter where they're going to fly to the USS Hornet that's on its way to this splashdown location. So this whole process, they splash down about 20 or 30 minutes later. This helicopter arrives. In that meantime, the command module has to upright itself by inflating these sort of inflatable balloon type things. It's an inflatable collar. It puffs it up so that the command module's in the correct orientation in the ocean. It's not flipped upside down. And then the helicopter comes in, puts everyone on a life raft, cleans them down. They board this helicopter, and then they're going to fly to the USS Hornet. So it flies over here to the Hornet, and if I jump to another stored view, I'm going to jump to the crew on the USS Hornet. They come in here, and then they are going to land on the USS Hornet. These models are actually just the default in STK. In the other recreation I have, we're using the real models there. But it would look something like this. After about an hour or so after they land, they're actually on the Hornet, where they will spend. They're going to go into something called the mobile quarantine facility, where they're going to spend 3 weeks in isolation, and that actually gets transported to Hawaii and then back to Texas. And just to give you a real quick, a little more detail about that whole. How much they're worried about the lunar germs is when Mike Collins was asked in one of his interviews, weren't you lonely on the far side of the moon? He's like, no, I had plenty to do. But what I was really worried about were the white mice. So once they get back, this was the first moon landing, the first time they actually had samples from the moon. So they put the lunar dust on the mice to see if they had any bad effects. And luckily, everything was safe. There were no lunar germs. But if there had been, the crew would have had to stay in isolation for even longer than 3 weeks, and that would not have been too fun. So I kind of skipped over this reentry part here. I'm just going to run through that real quick. And there's a couple more steps down here we can real quickly wrap up. But that, I'm actually probably just going to skip over that. The instructions are in the PDF, and what those are is just running a few graphs to compare the reentry profile to the planned of Apollo 8 profile right here. And what you can see during the splashdown and the altitude is the peaks and the drag. So there's a drag graph that's going to get run. You'll see a peak here and a peak there. So we know we're kind of, we modeled that fairly reasonably. We saw the same drag peaks, and the altitude profiles match this one. There's a few more steps here that are updating the helicopter's performance model. So if I go ahead and open up the aircraft, this is Swim 2. I'm just going to show you how that was modeled. They have a reference state here. They fly to the splashdown, they hover, and then they go and land on the aircraft carrier. What you can do is actually update this basic helicopter performance model by clicking select aircraft. You can duplicate this and update some of its properties. The steps are given here, and what we did was what we could do is just update the ascent rate as well as the maximum airspeed. So that's all what we would do there. It doesn't really change this profile very much, but you can customize your helicopter or your aircraft to be more specific to your particular needs. So that's one last thing. And to wrap everything up, to leave you guys off with a pretty picture, just to also recap what happened through this entire mission. If I go ahead and close this property panel, let's just look at the entire trajectory one more time as a whole. So if you go to the Earth-Moon rotating view, this other 3D graphic windows that wasn't used very much, click the drop down and then click on Target Overview. So this is on page 51 of the PDF. So if we have this set up, then we're going to open up the properties of our service module. And then we're going to come down to where it says Pass, 3D Graphics Pass. And then Orbit lead type, we're going to change that to be all, and trail type to be all. Then we're going to click OK. And what that does is it shows our entire trajectory from start to finish. And we're going to add one more thing. If you go to the properties of our Earth Moon rotating view, we're going to click on the Access Text tab. Then we're going to click Show. And then we're going to come down here and click the Earth button. And then we're going to find the service module. And then go ahead and make sure all of these are checked. And then we're going to click OK. So what we did just right there was turn on these this data display for the access text. And that tells us when the service module could see the Earth. So as they're going through the mission, we're just going to animate. You can see them actually go to the moon, circle behind the moon. You'll see times down here where they will lose access to the moon. You can see when they last had sight, when they acquire sight again, as well as this drop down. And just wanted to leave you guys off on a note where you can see the entire Apollo 11 trajectory. And thank you again for coming. Congratulations. You've now modeled the first historic moon landing. Thank you. I'm going to turn it back to Craig.
Thanks, Austin. That was really informative. That was really interesting. Probably one of our cooler ones that we've ever done. That was a great series. Thanks, Austin. Again, we have all of the previous versions, the part 1 and part 2 on our website at agi.com/Apollo11. We also have some other interesting things on there about Apollo 11. We're running a blog series about some of our engineers and what they were experiencing during the time that Apollo 11 was going on. So check that out too. So on our website, agi.com/training is going to be where we're posting up our new virtual trainings. We have a new summer series coming out soon, as we're going to call it the Summer School because we are very clever. And the Summer School is going to consist of space environment. So that is going to be our 4th track in our STK Grandmaster certification. Again, if you have any questions, you go home, you start thinking about this training, you want to ask us something, you can always contact us at 610-981-8888 or email us at support@agi.com. We look forward to hearing from you. We didn't get a lot of questions today, but I think that's because Austin was a great teacher. But if you do go home and you start thinking about things, let us know. Again, support@agi.com or 610-981-8888. Maybe Austin will answer those questions. We don't know. Again, we're going to remain on the line 10 more minutes, so send those questions in. If not, I hope to see you at an upcoming virtual training event, especially for our summer series. Who doesn't want to spend more time with me? I don't know. All right. Again, thanks. And again, hope to see you soon. Austin wants to say something else.
Thanks, Craig. Yeah. Could I share my screen as well?
Sure. You want to start? That's fine.
That'd be great. Yeah, so just to wrap up those few things for the to wrap up on time, I just wanted to real quickly highlight some of those graphs. Went ahead and random. Again, the instructions are on page 47. Some of that reentry profile, you can see our drag, a drag profile here, and then these went and peaked just above 5, almost 6 G's, and you can see the drag force peak here, which is similar. The times in which this occur are similar to the Apollo 8 plan profile. So that was just another confirmation that we came in pretty similar to how they did during the actual mission. This is the drag graph on my left with the peak G-forces, and over here on the right, this is the altitude versus downrange as in this figure for the Apollo 8, which is a very similar profile to the Apollo 11 reentry graph. So this is altitude on the y-axis and downrange here. And these two graphs are inverted, but you can see they kind of follow this pretty similar path here. Okay, so if I just close that guy, I just wanted to wrap those, show that for the camera, which is, again, in the instructions. And then the last couple phases, apparently we had a question about a model, but we are going to go and update the aircraft performance to account for the actual helicopter that was used, which was a Sikorsky Seahawk SH-3, and we just updated. We would have updated the altitude ascent rate as well as the max airspeed. It doesn't have too much effect on our trajectory here, but you can go and tweak those performance characteristics. So, Craig, were there any other questions on the line?
No, that looks like it. That might be it. So we'll close it down. Again, the resources to get a hold of us, 610-981-8888, or email us at support@agi.com. Again, thanks for attending, everyone, and see you soon.